Sorry about that. My voice is a little dry. Okay, good morning, everyone. I wanted to talk this morning about two topics. It's kind of a two-for-one. I'll talk a little bit about the new facilities that we have planned for construction to begin probably in a few weeks over in Building 31, just across the street. And then I'll talk a little bit about the connection between samples from these two bodies and the Antarctic Meteorite Collection. Anyway, the point of this slide is that the long history of astromaterials collections at JSC is about to be enhanced by the addition of samples from two asteroids, as you know, Ryugu and Bennu. And we're building a facility to two different clean rooms to house these samples when they come back. The Ryugu samples are expected at JSC through an MOU between NASA and JAXA. 10% of what is collected will be at JSC, which is a really great opportunity. And then the OSIRIS-REx samples, as you just heard from Dante, will be coming back in 2023. Okay, so Dante gave such a great, of course, no surprise, great introduction to OSIRIS-REx that really I can skip over this, but I just want to re-emphasize that the samples will be returned in September of 2023 here on the timeline. And so we're all really excited about this, of course. The JSC role, curation role in the mission has been pretty extensive, going back already, well, we've been working on this for 10 years, really, but our real activities started about 5 years ago. I won't talk about all of this today, but I wanted to talk about briefly the first collection that we already have in place at JSC, and then I'll talk about the new clean room suites that are being constructed at JSC. So the first collection that I refer to is a large collection of materials that we've archived in connection with the construction of the spacecraft, materials that were collected excuse me, during ATLO, and so that as the spacecraft was built, and in particular the sampling hardware and mechanisms, they experienced many different environments, and all the way through till the launch pad. And so we have collected materials from the spacecraft of a wide variety, and from various components on the spacecraft. There are over 400 items that are archived now at JSC. And in addition, well, a couple examples like some honeycomb composite from the solar panels shown here, and then a vial of lubricant that was used in one of the instruments is shown here. There are lots of stainless steel parts and aluminum parts and so forth. Epoxies, we've got them all, and they're kind of reflected in this table here. But the other thing that we have is a set of witness plates that are archived, and these witness plates experienced all of the clean room environments that I showed in the previous slide during ATLO. So all of these materials are now in a lab in Building 31N, the Return Sample Vault Lab, and two dedicated cabinets, nitrogen cabinets. And if you want to learn more about this effort, it's explained and described in more detail in a paper by Dworkin et al. That came out last year in Space Science Reviews. Okay, so the second topic for this morning related to curation of these new collections is the actual facility. So if you're familiar with Building 31 here, so there's the high bay where all the research labs are, there's the main building, and then there's the 31N where the lunar and the Apollo samples and Genesis samples are. In the sort of the southwest half of Building 31, both the first and second floors are about to be renovated, And the second floor will contain the suite of clean rooms shown here, one of which will be for OSIRIS-REx on the left, and one of which on the right here will be for the Hayabusa 2 samples. And then we have some shared, dedicated entries and a shared anteroom and a microtomy lab as well, part of this suite. So this, as I mentioned, this will start in a few weeks. Should take much of 2019, and probably spill over a little into 2020. And I'm looking at Lisa Pace because she's staying on top of this incredible schedule. Let's see, the labs are starting, you're probably thinking, well, it's 4.5 years till OSIRIS-REx gets back. That's true, but we're expecting Hayabusa 2 samples in 2021. And so we need to have the labs finished, completed, certified, well understood, and characterized before we introduce samples into them. And so hence that's driving the construction schedule. And then for OSIRIS-REx, we, knock on wood, will be easily meeting this deadline of being completed a year before samples are returned, and that'll allow us to do outfitting in the labs, carry out rehearsals, and do some monitoring and so forth. And then one thing I won't talk about, but I'll mention, I won't show you in detail, but I'll mention directly below this lab, or this clean room suite on the first floor, will be a new series or suite of labs supporting advanced curation and advanced cleaning that'll be benefiting all of the collections in the curation group. That will be carried out at the same time as the clean room suites for the samples. Okay, so let's see, we'll begin, once the lab is done, we'll be outfitting, and we'll be outfitting the labs with, processing cabinets and storage cabinets that are sort of pictured here. Of course, it's too early to show you the actual cabinets, but we'll be working on designing the cabinets to meet the needs of the various sample types, which I'll show you in a minute. And we'll also be doing a little bit of preliminary non-destructive characterization in the labs as well, so we'll be outfitting to support that. So what materials will be curated? So there are really four main types, and I'll just briefly touch on each of these. There'll be bulk sample collected in the tag SAM head. There'll be contact pads, which Dante showed at the end of his talk, the 24 little Velcro pad, stainless steel Velcro pads that are around the bottom of the tag SAM head. There'll be witness plates that are located both on the tag SAM head and in the sample canister that'll be witnessing the environment the sample sees. And then there'll be some hardware items that are removed as well and curated, one of which is the air filter at the top of the canister. So a little more detail about each of these. The bulk sample will be collected within the tag SAM head, and this is the result of one of the tests that was done at Lockheed, showing how much material we might expect. And they've done, this is just a subset of the tests they've done. They collect as much as 1 kilogram of material, so it's a lot of material potentially that could be packed into the bulk sample head. Okay, the other second kind of sample is a contact pad, and these are a little more detailed images courtesy of Christopher Sneed, who's been experimenting with the contact pads and various kinds of simulants. And you can see that these pads are made of these little stainless spring steel hooks, which capture material like this larger piece, as well as a lot of fine material. And Christopher has been experimenting with how to remove material from these springs. And we'll do more of this kind of testing as well, but this is a good start for this particular sample suite, which will sample the top portion of the regolith. The third kind of sample is, as I mentioned, are witness plates. And here, you can see these circular plates around the top of the tag SAM head. around the outer perimeter, and there's a series of 6 here inside near the wrist or the wrist of the tag sand head. And then there's some also witness plates within the canister shown here and in some other locations as well. Oh, here, they're shown here as well. So we'll be curating those in dedicated cabinets in the clean room as well. And then finally, we'll have some hardware. The filter is the most significant one. This is a 2-way filter that protects the samples from the contaminants outside and can also trap gas that may be released from the sample on the inside. So we'll remove this early on and give it a special treatment and processing as well. Okay, so as we get closer to the samples returning, there's the activity in our labs will ramp up, and what we've started already, I mentioned Christopher's work with the contact pads, but he's also been working on handling small particles, moving them around, and we may have millions of particles like this, literally, to deal with, and so we need to become more proficient at sample handling and characterization, something new for us, and we've gotten a start already. Okay, so just to drive that point home, we'll be doing a couple of detailed rehearsals as we get closer to recovery, and we'll have some of the hardware at JSC so that we can do our own in-house characterization and testing as well for the next couple of years. Okay, so that's part one. So as I said, we're really excited about getting these new samples. We can kind of whet our appetites a little bit by looking at meteorites that we have in our collections. And so I just wanted to give a brief overview of the meteorite collection and then show some connections that have already been made to carbonaceous meteorites and perhaps relevant to Bennu and Ryugu. So the Antarctic Meteorite Collection is growing every year. It's currently at almost 23,000 meteorites in the 41 expeditions since 1977. And most of these have been classified. They come out in newsletters announced twice a year, and it's the largest research collection of meteorites in the world. So it's a great honor to be associated with this collection, which supports so much of planetary science. But I'll focus on a couple of specific bodies today to draw the connection between the two. So just to give you an idea, a couple of snapshots during the history of this program. In 1995, there were 29 dense collection areas where meteorites had been returned. The collection was about 8,000 or 9,000 meteorites. Now with this recent completion of the recent season, just a week ago, the field team, 2018-2019 field team, recovered 865 new meteorites. You may or may not have heard this. It's pretty new news. They were in the Dominion Range area, and as of now, we have 52 dense collection areas, and as I mentioned, the collection is close to 23,000 samples, so pretty large. So most of these are chondrites. There are around 700 achondrites in the collection. I won't talk about these today, but we don't want to ignore them. The chondrites, though, among the chondrites in the collection, many of them have helped to establish some of the more interesting chondrite groups, some of the carbonaceous chondrite groups like CHs, CRs, CBs, some of the enstatite groups like the one shown here, MAC88 136 is the EL3, was established primarily by Antarctic meteorite samples and some of the R chondrites. So I want to talk a little bit about some of the CM chondrites that we have. And first of all, I mean, I could this is a huge topic. I could go on forever probably, but I'll just highlight a couple of studies. That the collection has really been integral to systematic studies of spectral features and aqueous alteration in cmchondrites. And there are a couple of studies shown here: reflectance IR, reflectance spectroscopy, transmission IR studies by Beck, Garan et al. And Takir. And there's a study here by Howard on some of our cmchondrites using X-ray diffraction and kind of characterizing the mineralogy of these really ultra fine-grained samples that are otherwise difficult to characterize. So if we think about Bennu and Ryugu, Dante showed this image already of the Bennu infrared spectrum and the 2.7 micron feature. So if you look at this study by Garan a couple of years ago, here are probably 20 different cmchondrites from our collection, all of which have this 2.7 micron feature. All of these are slightly different. And so my only point is that I'm hoping that our collection can help to interpret these spectra, and we'll get more detail, I guess, as we get closer in, and spectral features from various geographic features will be available, and I'm hoping the collection will help with the interpretation. So here are a couple of analogs that you've seen. You've seen these numbers and plots. Here's what the samples look like, hand samples in the lab. And then some of the thin sections, you can see how fine-grained these samples are, and some of the mineralogy that's been determined. These are dominated by phyllosilicates. So if you're wondering what a lot of the black material is in these thin sections, it's anywhere from 70 to 100%, almost 100% phyllosilicate material. Okay, so just quickly about Ryugu. So in comparison to Bennu, Ryugu has a very weak hydration feature that's been discussed by the Hayabusa 2 team. And this might mean that the Ryugu samples are dehydrated relative to your typical cmchondrites. And there's a small but growing collection of these heated CMs, which have slightly lower carbon, slightly lower hydrogen content, slightly higher reflectance than your regular CMs. And so we have a number of these in our collection as well. These three are just examples of anomalous CMs in that they show evidence for heating or metamorphism. And again, you can see what they look like in thin section. They're also phyllosilicate rich, so they're not exactly dry. And so again, I'm hoping that these will help with the interpretation of Ryugu as well. Okay, so this is just a summary of the two parts of the talk, and I'm happy to take any questions you might have. Thank you.
Questions?
Just an observation. Phyllosilicates are not dark, so what is driving the darkening factor in these things?
Yeah, that's a good question.
Could you repeat that?
Yeah, what's driving so phyllosilicates are not dark, and therefore what's driving the dark color in the samples, and I guess in the asteroids as well, right?
Presumably.
But yeah, presumably. It's a lot of times the darkness is caused by fine-grained sulfide, and you see that in impact melts for sure. Finely disseminated FES throughout samples. That can cause a darkening.
Well, but you also have a lot of magnetite.
Yes,
You have a bunch
there's magnetite.
Organics.
Yes,
And so,
could be all of those working together.
yeah.
Any questions on? Okay, Andy Rifkin.
Yeah, this is. Were there to be some miraculous rapprochement between the U.S. and China, and it worked out that China agreed to send lunar samples to the U.S. to be curated, how quickly could you accept those samples pretty easily, or would that require a whole other set of buildings?
I don't, does anyone else want to field that question? I'm not sure.
Say anyone, Say, I mean, if there was some foreign, agreement made by some country that was going to the moon and bringing something back.
Yeah.
Would that get private? Sure.
Yeah, the moon.
Or private companies.
We wouldn't be able to accept that, and it wouldn't be very hard.
Yeah, the lunar lab has capacity.
Could you repeat?
Yeah, so the question is, if a collection of lunar samples from another entity, whether it's a country or private enterprise, offered them to NASA to curate, how quickly could that happen? Could it happen, and how quickly? Yeah.
Pretty quick.
Yeah, pretty quickly. So I know that just from discussions I've been involved with over the past 15 years, the advantage with lunar samples is that it's possible that part of the Building 31N could be converted to house such a collection. So it's a little easier. It may not require construction of a new facility, for example, or a new clean room. It may just require modifications or upgrades, so which should take less time.
Okay. Thank you, Kevin. Thanks, Kevin.